let's get on with that. So here's a question for you. Let's get the font big enough and read it a bit. Right. Xavier and Yvonne are noisy, badly behaved siblings. Also, their names begin with X and Y, which is going to be handy. They argue about whose turn it is to play with the computer, which they are supposed to share. Hoping for a quieter life, their parents want you to build a machine to settle disputes. They have plenty of standard logic gates and 2 flip-flops. One is a D flip-flop, the other a T flip-flop. Okay, now, because I know flip-flop questions are hard, I try and give away some marks at the beginning for just reciting lecture material. So the first thing we're asked for is the characteristic table for a D flip-flop and the truth table for a T flip-flop. So can we remember about characteristic tables? What we're being asked for. So for a characteristic table, you just tabulate the control signals. And then you explain what happens to the output at the next step in terms of the current state of the flip-flop. Sure. I can zoom out a little now that I'm not trying to read tiny text. Okay, so we tabulate the possible D signals, 0 and 1. So when D of t is 0, what will Q of t plus 1 be? 0. And when D of t is 1, what will Q of t plus 1 be? 1. Okay. When we're asked for a truth table, and we are asked for the truth table for the T flip-flop, we have to write not only the control signals, but also the current state. So we tabulate all of those, and then we give the new state just as a bit. So characteristic table, you give the new state as a formula. Truth table, you give the new state as a bit. So tabulate all possible situations. Okay, so help me out here. We are not sending the toggle signal, and the current state is 0. What's the new state? 0, because we're not toggling. We're not sending the toggle signal, and the current state is 1. What's the new state? 1. We are sending the toggle signal, and the current state is 0. What's the new state? 1. Yep. We are sending the toggle signal, and the current state is 1. What's the new state? 0. Okay. So the next thing we're asked to do is to show how to construct a D flip-flop from a T flip-flop using one standard logic gate. So we need to build D from T. Okay. So in order to figure that out, it's actually a good idea to draw a truth table. We can find ourselves in any of these situations. Okay, and we know what new state we want. So now what we have to do is figure out what T signal would make this change happen. Okay? So if we want this T flip-flop to go from 0 to 0, what signal do we need to send in on T? 0. We're not toggling. If we want it to go from 1 to 0, what should we send in? 1. If we want it to go from 0 to 1, what should we send in? 1. And if we want it to go from 1 to 1, what should we send in? 0. Okay, so this now tells us that if we know the current state and we know the D signal we want to obey, what T signal we should send. can you think of an appropriate piece of circuitry that would deliver this T signal given D and Q? XOR. So what that tells us is that we should build a circuit like this. Here's our T flip-flop. And we figured out that the T signal, in order to get the behavior of a D flip-flop, we figured out that the behavior we need to send in, the signal we need to send to T, is the XOR of D and Q. Can everyone see where that came from? At any given time, we want T to be the XOR of D and Q. So this circuitry, where we wire Q background into the XOR gate along with D and feed the output of that into T, that will generate the correct behavior. The whole circuit will behave like a D flip-flop because we've got the extra logic right. So that's an example of what happens where we wanted to get the D behavior from a T flip-flop. We can't just send in, T doesn't natively do resetting or setting. But we can use logic to figure out whether it should toggle or not in order to behave like it's setting or resetting. So that's what's going on here. Okay, everybody fine so far? Because now we get, so that's, I'm hoping by that stage to have given 3 marks away, which is sort of exemption standard. And then we get a tricky puzzle for the last bit. Okay, so this is quite typical. There'll be a pile of text that describes in words the rules of some situation. And you need to read it and understand it and then figure out how to turn it into some sort of table that will express what's going on. So I know some of you have issues with reading questions. It's sort of, when at school you're kind of taught to react to questions that you recognize and kind of go into a formulaic way of producing an answer. I'm afraid that won't do. The questions will not be formulaic. You will need to read them rather than just react to them instinctively. Okay, so let's read the question. At any given time t, the input signal x of t shows whether Xavier is requesting to play. The output signal qx of t shows whether Xavier is enabled to play. And similarly with y of t for Yvonne and qy of t. Show how to construct a machine which implements the following rules. Well, first of all, Xavier and Yvonne cannot both be enabled to play at the same time. So that tells us that our two flip-flops had better not both be one at the same time. They better not be given a one output. That would send a confused message. Okay? Whoever is enabled to play remains enabled for as long as they request to play. So that's to say, if qx of t is 1, if Xavier is already playing and he presses the button to say he wants to keep playing, he gets to keep playing. Same for Yvonne. If neither requests to play, neither will be enabled. That's only sensible, right? If they don't actually want to play, they shouldn't have to. If just one of the two requests to play, they will be enabled. That's also reasonable. If there's no contention, then whoever wants it should get it. If both request to play, but neither is enabled, Yvonne becomes enabled. That's to say, if neither of them is currently playing with the computer, and then both suddenly say that they want it, Yvonne will get to play with the computer, and Xavier will just have to wait his turn. Okay, so we've got a blatant piece of positive discrimination in order to deal with the contention. Okay, so The question further says, it may help to draw a suitable characteristic table. So let's just think about what happens. So we can, if we tabulate what they want to do at a given time, then we can figure out what they get to do at the next point in time. Okay, tabulate all possible signals from the buttons. Right, so let's figure out, let's interpret the rules as the appropriate entries of this table. Okay? So if X and Y are both 0, that means neither wants to play. So neither ends up playing, right? We should put zeros here and here. The next row is Xavier does not want to play, but Yvonne does. So there's no contention. And Yvonne gets to play. On the next row, X is 1 and Y is 0, which means Xavier wants to play and Yvonne doesn't. Again, no problem. Xavier gets to play. So, now we get the hard part. In the last row of the characteristic table, we have Xavier and Yvonne both wanting to play. Under what circumstances will Xavier get to play? If he's already playing. There's 3 possibilities. Either he's already playing, or Yvonne's already playing, or neither's already playing. The rules say that in those situations, if Yvonne's already playing, he certainly doesn't get to take over. If neither is already playing, but they both want to, the rules say Yvonne wins. So Xavier only gets to play in this situation if he's already playing. So that's to say Qx of t is the correct thing to put here. That's to say, if he's already playing, then he gets to play at time t plus 1 if he's already playing at time t. And under no other circumstance on this row of the characteristic table. Under what circumstances, assuming both Xavier and Yvonne want to play, under what circumstances will Yvonne get to play?
She's already playing or neither.
Yeah, if she's already playing or neither of them is already playing. That is to say, in particular, if Xavier is not playing. Okay. So now we know the behaviors that we want. We need to build some circuitry that will get us there. Now, we've already explained how to build D from T, so we can assume that we can just do this with 2 D flip-flops. So we've got, let's call them dx, qx, and dy with output qy. And we've got signals x and y coming in. Okay. We need to get the logic right. When should we, so you know that whatever qx of t plus 1 is, that's generated by whatever dx of t is. And that's dy of t. So what this table is really telling us is the correct logic for choosing dx and dy given the current situation. So we can see that, in particular, one condition for either of them to get to play is that they want to play. So we can code that up easily enough. I'm just going to stick and in there. And maybe I'll regret drawing that line in that place. Stick an and in there. Okay. So, what apart from Xavier wanting to play means that he gets to play? Well, so in particular, that's one of the situations, yeah? So one of the situations corresponding to this line of the truth table is just Yvonne doesn't want to play. That's one possibility. So let's have it or. And we'll stick that, not y. Okay, and now we've got to figure out what's the other possibility? Yeah, qx is 1. Okay. How about Yvonne? Let's suppose that she wants to play. When does she get to play? Well, how do we code up this row of the truth table? We're already checking that y is 1. What else do we have to check? That x is 0. So we're on this line of the truth table if x is 0. So I'll stick another or in and another not. And I'll wire x to that. Okay. What about the bottom line of the truth table? Well, it's not q of y that needs to go in. It's not q of x. So it's not completely symmetric, remember, because the rules are designed to break contention in favor of Yvonne sometimes. So what needs to go in to the other possibility is not q of x. Okay, so let's just check that we believe this circuit actually codes up the rules, codes up what we've written. dx will be 1 when x is 1 and either y is 0 or qx is 1. Meanwhile, dy will be 1 if y is 1 and either x is 0 or qx is 0. So either Xavier doesn't want to play or he isn't currently playing. So we've coded up the logic correctly. This is the right circuitry to control the flip-flop. So this is how you figure it out. You first of all interpret the rules as the behavior that you want to happen, the behavior that the rules say should happen, and then you figure out what signals you need to send to the controls of the flip-flops to make that behavior happen. So loads of flip-flop questions are like that. First of all, figure out the behavior that the rules tell you you should have, then figure out what control signals will produce that behavior, given the flip-flops you've got. And then then it turns into an ordinary build a circuit with this logic. problem. So that's what's going on. Okay, so that's an example of a typical flip-flop problem. And you've got 2 of those to do for your homework, which I hope, well, I mean, I know that flip-flops are always a tricky topic, so it's important to make good use of tutors in that situation. After a while, there's only so much one can do in a lecture situation. You just have to try problems and get help with them. Because learning by sitting passively in a lecture room, I'm well aware that this may be where teaching happens, but it's not where learning happens. Right? Learning happens when you try, fail, engage with the problem to the extent that you're ready to receive some explanation about it. That's why we have tutorials. Okay.